So now next we have what? We have the we have the addition of hydrogen halides to our alkenes. So um, and alkynes, right? So let's take a look at those reactions. So what's a hydrogen halide? So that's some sort of H with a halogen compound, right? So that we add to our molecule of alkene or alkyne. So let's take a look at what happens, right? So again, here are a couple examples. So for example, maybe we're going to have something like relatively simple, such as this alkene, right? So that's going to be our ethene, speaking of nomenclature, right? So ethene, and then we add HBr to that. So HBr, so we show the bonds, which are going to be broken explicitly. And then we'll show the bonds which are going to be made, right? So we'll have CH2 connected now with a single bond, CH2. Then you have here your
attention, please. The time is now 4.
So the CH2 and H bond will be made, as well as CH2 to Br bond will be made, right? So electron, 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 electron. Here we go. You make two new covalent bonds, right? So this is again a topic we have seen in the past. So now let's take a look at alkyne, right? And then we're going to add two HBr molecules right away to that guy, right? So the alkyne will be looking like this. So let's say we're going to have CH3 carbon now with a triple bond to another carbon, right, with a triple bond. So CC carbon-carbon triple bond, as they call it, right? So that's the signature of an alkyne. So then you have another methyl here, and then you're going to add 2 HBr, for example, right? So let's just use stoichiometric coefficients now. You have HBr and HBr, or 2 HBr, right? So then what's going to happen is that this bond will be broken, this bond will be broken, and then total of 2 HBr bonds will be broken, right? So it turns out that basically those H's and bromines will go to the carbons in a specific fashion, right? And then essentially what's going to happen is that you are going to have 2 electrons here, right? So that will make basically 2 CH bonds, right? So here we go. Let's draw them. So CH3, this central bond survives. And now you're going to have CH bond and CH bond, right? So that's the 2 H's that came from 2 HBr molecules, hydrogen bromide. So don't forget to redraw the parts which don't participate in the chemical reaction. They still carry over to the final product, right? So now you're going to have here 2 free electrons, and you have also Br with a free electron and another Br with a free electron. Let's put them together. You have CBr bond number 1, and you have CBr bond number 2. That's it. So, next one. Let's take a look at some specific rules, right? So here we're looking at some kind of like symmetric alkenes, right? However, some alkenes can be quite different, right? So, and in that case, we're gonna decide where is our H and Br, for example, are gonna go in the case of addition reaction, right? So addition of HBr or hydrohalogens in general, or water, right, for that matter. So let's imagine that we're going to deal with the one propene, which is going to be looking something like that. CH2, double bond, CH. So here we see the asymmetric alkene already, right? So because it's not like CH with methyl, and here we have double bond, CH with a methyl, right? So that would be symmetric, right? 2 butene, by the way, right? So now we have one propene. And let's imagine we're going to add HBr to that, right? So here we're going to guide ourselves with the Markovnikov's rule, which says basically that when we see this kind of like non-symmetric alkene, so what's going to happen inevitably that this one of the carbons will have more H's, the other carbon will have less H's. And it's going to be like apples to apples, pairs to pairs, right? So basically, the H from the hydrohalogen or water, by the way, which we'll see later on, the H will go to the carbon with more H's, and bromine, by extension, will go to the carbon with less H's. That's it. Still, the carbon-carbon single bond will be broken. The other bond will prevail. HBr bond will be broken, right? So 2 H's on the left carbon, 1 H on the right carbon. That's it. So the H will be obtained by the leftmost carbon. As a result, we're going to have the following molecule. So CH2, right? So now let's explicitly show the bond, right? And of course, we can call it just CH3, right? So, but now we're going to show the bond that is made between the carbon that gets more H's, right? Because it used to have more H's. So the carbon with the more H's will get an H. So now it turns from CH2, because it has more H's, right, to CH3. This carbon with less H's will obtain the halogen. So it will turn from CH to CHBr. And now we have, at the end of the day, a substituted alkane. And then we will not have bromine here and H there. So that's not observed, right? So this is going to be our product that we are going to obtain as a result of this chemical reaction. So this is Markovnikov's rule, right? Markovnikov's rule can be also applied to the case of hydration of alkenes, right? That's going to be our ultimate reaction here that we are going to show for alkenes. And this reaction, the hydration, addition of water molecule, doesn't apply to alkynes. So let's show it with alkenes consequently, right? And then we are going to show it right away using some sort of interesting example, right, of an alkene. Let's do it this way. So let's imagine we have an alkene like this, right? So CH2, and here we have a couple methyls, right? So that's going to be our relatively complicated alkene, right? So in this case, we're going to see the substituted alkene, right? So it's like a chain with a substitution going on. Okay, great. So ultimately, this is going to be like a non-symmetric alkene, right? So from one point of view. And then we will see that we're going to add HOH. We're going to show water as HOH specifically because we're going to show that this bond is broken and the respective parts will be added to the liberated electrons of the broken single bond that is present inside the double bond, right? One bond will stay, don't touch it. The other bond, yes, you can put a squiggly line in between, right? So in between the two electrons that make this single bond. So now here you also have the squiggly line, and now you need to decide where does H go, where does OH go, right? So the hydrogen from the water will go to the carbon according to the Markovnikov's rule, right? It will go to the carbon that has more H's. So consequently, this hydrogen will go to this carbon. That's what will happen. The OH piece of water with a free electron on oxygen will go consequently to this carbon, right? So that's it. That's what we are going to have. Now let's show the product. So by the way, this, as we know from our textbook materials, this reaction is executed in the presence of H2SO4 as the catalyst, right? So now let's show our final product. We can reposition the drawn pieces a little bit. CH2, having more H's, will get an H. This carbon, right, so we'll get OH. That's it. This is your, by the way, alcohol. You just made an alcohol because you have COH piece in this molecule, right? So then you have the alcohol functional group present in this molecule. So this is going to be our hydration reaction that follows the Markovnikov's rule.